Okay, guys, welcome back. Now we're on to landscape evolution. This lecture is going to try and combine almost everything in the class. I hope it's successful. I get a kick out of the topics that are covered here. I hope you guys enjoy them as well. So what the heck is landscape evolution? All it is landscapes change and develop over time. They're never static. They're always dynamic. If you were going to learn one thing from this class, I hope that's it. Landscapes are always in flux. They're always changing. I think this picture is a good example of it. This is Zion Canyon up in Utah here. This is the Hurricane Fault running through here. It's a big, massive normal fault. These are antecedent streams here. You got Grand Canyon in the background. You go forward 5 million years in time, this looks totally different in the future. The definition of landscape evolution is the overall topographic alteration of continental surface, SIS, from their tectonic construction to their weathering, hill slope fluvial, and other process-driven erosion. Okay, so landscape evolution is geomorphology. I mean, that's the crux of it. I hope I've done a good job explaining the different components. I've tried to tie in the rock cycle. I've tried to tie in the hydrologic cycle in terms of how all these things work. The general idea is rock cycle inputs rock into our continents, building mountains. The hydrologic cycle and gravity acts on that rock, weathers it at first, then hill slopes move it down, then rivers take it back out into the ocean basins. How all three, these two cycles interact with each other generates our geomorphic system, or what the surface of our planet looks like over time. All right, so let's give this a go. So here's a question for you. What would a landscape look like if weathering rates, so that rate of breaking down of rock, is greater than the rate of hill slope transport? So the rate of breaking down and the in situ breakdown of rock is greater than the rate at which hill slopes can move it away. What's the landscape going to look like? Think about it for a second. It's going to look like this. All right, what you end up with is a transport limited landscape. When we were talking about hill slopes, that's known as an any hill slope. And that's because the weather material piles up on the hill slope itself, and it acts like a sponge and it absorbs all the water, and you don't really get any channels on the surface. Okay? If you want to enact change on this landscape, you need to alter the rate of hill slope transport. Weathering's having no problem at all generating weathered stuff, hill slope's struggling to move it off. You can think of it like a supermarket with too many goods. So you can imagine, it's not what he's doing, but imagine this guy going out there and he's just loading stuff up onto the shelves and it's falling over and nobody's coming through and buying it. Okay, the customers would represent the hill slope processes. He represents the weathering process. He breaks this stuff's supposed to be the weathered rock, the broken down stuff, and it's just full of stuff, and we're waiting for hill slope processes to kind of flush all this stuff out. Transport limited landscape, also known as an any hill slope. Okay, what would a landscape look like if weathering rates were less than the rate of hill slope transport? So we're generating, our capacity to generate weathering rock is less than the capacity of hill slopes to move it. And as you probably guessed, it's going to be the opposite. It's an outy hill slope. Okay, it's a very clean hill slope. You have a lot of rills, small channels on the surface, bare bedrock. Whatever weathering generates, boom, it's gone. It's getting moved off. No problem at all. Landscape change depends on the rate of weathering. Whatever weathering generates, it's gone. Any particles generated through weathering are easily transported by the fluvial systems. It would be like a supermarket where there's hardly any goods being put on the shelves, and whatever's put on the shelves, people are coming through and buying it, and you end up with very clean looking shelves. It's a weathering limited landscape, identical to an outy hill slope. Okay, what would a landscape look like if hill slope transport was less than the rate of fluvial transport? So again, a landscape, the hill slope transport is less. So the rivers have the capacity to move more stuff than what the hill slope is generating. What you're going to get is a pediment. And this is a tough image to visualize, but this is actually a diagram I made. So imagine this is a mountain in the past. very steep. And here's the mountain, and then here's the alluvial surface, the river surface coming off away from the mountain. Okay, and the slope of that river is constant because whatever this mountain generates, the river just moves it off, no problem at all. But as that mountain erodes, the hill slope maintains its slope because that's its rate, that's the slope it wants to move its stuff. The river maintains its slope because that's the slope it wants to move its stuff. And so the mountain front retreats back over time. But what you end up with is this shelf of bare bedrock surrounding the mountain. That's what these pluses represent. That's supposed to be the bedrock that's now exposed. This is a plane of bedrock that wraps around the mountain. Okay, they're cool. They're pediments. I love these features. Here's the Santan Mountains. You can see surrounding it is a nice pediment wrapped around the mountain. Here's a granitic mountain with a nice pediment here in the foreground. You can see it's all bedrock. Here's an example of bedrock exposed at the surface on a pediment that's being eroded. This is kind of cool. So if you go back to the last diagram, imagine we had a big mountain here in the past and it's retreating back. Well, eventually the mountain will just go away. You'll just erode it. And all you're left with is the remnant pediment. Okay, that's all that's left, and it's known as a pediment dome. That's what this feature is. All that's left is the remnant bedrock shelf that are wrapped around the mountain. And now the mountain range is gone, and all we have is that bedrock dome. Cool. Okay. What would a landscape look like if hill slope transport was greater than the rate of fluvial transport? So this is going to be the opposite. And what you end up with are alluvial fans. So here's the deal. Hill slope processes are just boom. We're generating stuff like crazy. Oh, excuse me. All the weathered rock that's coming off these mountains, it's just getting dumped out. And the fluvial systems are just like, dude, I can't handle all this stuff. And so basically the mountains just get plugged up in all this sediment. Zones of hill slope deposits build a broad apron around the base of mountain fronts. Struggling fluvial systems utilize a secondary period of weathering to break down core sediment. That's supposed to be an A, not a U. Ugh. Because this stuff piles up so much, it's waiting for the rocks that are here to even weather even more before those streams are going to have enough energy to move them out. Wait for them to get smaller. Alluvial fans. Here's some images of Death Valley. Death Valley is famous for their alluvial fans. Another awesome landform. There's the two extremes. Pediments, clean mountain front, alluvial fans piled up in all kinds of rocks coming off the hill slopes. Okay, so now let's zoom in and look at our generalized landscape model. Okay, so we're looking at specifically this thing where we have sediments get dumped in the ocean, compacted to form sedimentary rock, cooked into metamorphic, melted into igneous, while magma that forms igneous injected back. What is this thing telling us about what our landscape will look like? So here's our first question. What is necessary for this landscape to be in equilibrium? And what I mean by that is, what would it take to have a mountain stay tall over a long period of time? Okay, say like 10 million years. What's necessary for this mountain to stay at the same elevation? All right, if you clicked with that, what it means is in order for a mountain range to stand tall for a long period of time, say 10 million years, you need a tremendous amount of rock to get pushed through the system. Okay, so this is in New Zealand right here, and this mountain range has been at roughly 10 to 13,000 feet for the past 10 million years. Okay, mountain range 10 to 13,000 feet tall, but it's been that way for 10 million years. But get this, the rock in the mountain range, 50,000 feet of rock in thickness have basically pushed through this mountain range, been weathered and eroded off in order for this thing to maintain its elevation over time. I call it mountain fountain. It's just like a water fountain where the water comes up and then it cascades off. The water comes up and then it cascades off. But the water is always moving through it, but it stays the same height. The same is true with mountains. The rock is always coming up and coming off. The rock is coming up and coming off, but the mountain maintains its elevation over time. I hope that blows your mind because that is so cool. Mountain fountain, people. Okay, So let's take another one. What could cause hill slope transport to accelerate rapidly? What could cause hill slope transport to accelerate rapidly? All right, so there's a bunch of things that maybe you guys thought of. In this one, this is kind of a nice hill slope landslide right into a fluvial process. Right, this river is going to try and move all this stuff out. But if you had a big rainstorm, okay, and a big rainstorm basically decreased the cohesion of the sediment, increase the weight, it could increase hill slope rates. It looks like it's fog, but it's actually dust. And this is a picture of a hill slope during an earthquake. Earthquakes can trigger massive hill slope events as you shake the stuff and allow it to fall. And also fires. Fires burn trees. The trees have roots that are holding the weathering front in place. Once they're dead, this stuff is much more readily eroded and removed via hill slope processes. Check this out. Boom. So there's a big earthquake in Alaska. This is maybe 10 years ago. Right here off this peak and right here off this peak, they both released massive landslides cascaded off these mountains and dumped onto this glacier. Like, boom. Okay. How would the geomorphic system respond if weathering rapidly decreased? How would the geomorphic system respond if weathering rapidly decreased? What could cause this? Well, before we go forward, I guess the general answer is this. What controls weathering is the hydrologic cycle. So the more rock that is exposed to water in the atmosphere, the greater your rate of weathering. So basically, if this decreases, it's probably a drying. You're going to have a drying period. It could get cold, which also makes things dry, but you dry it out. And if you decrease the rates of weathering, you're not having as much stuff to hill slope, your mountain range is likely going to grow taller. Okay? If it gets wetter, it weathers more, your mountain range will shrink, which is kind of fascinating. And they've recorded that's what mountains do. They'll get taller during periods of dryness and smaller during periods of wetness. Amazing! Here's some images of mountains and areas to kind of help think about that. Okay, what might have occurred if deposition off the continent increased rapidly? So what we're talking about there is, what would it mean if rivers started dumping a lot more sediment off into the oceans? What's going on? In this case, it's the opposite. If your climate gets wetter, you're weathering more, hill slopes will push more, it'll dump more stuff into the rivers, and you're going to be dumping more stuff out into the oceans. So when you start getting a higher rate of sediments dumped in the ocean, that tends to indicate that you're in a wetter climate. Here's what it looks like when you're in a wetter climate. You don't necessarily get snow. Well, that's a cool picture. This is snow up on the McDowell Mountains. But you're going to get stuff like this. Bigger rivers moving more sediment, dumping it off into ocean basins. But your mountains get shorter because the erosive powers are better at moving the stuff out. Okay, what might the significance be if one side of a mountain weathered more quickly than another? And would this be common? So what I mean by that is, here's our mountain. We're weathering on this side and we're weathering on this side. But what would it mean if this area weathered quicker? Well, if it weathered quicker, deeper over here, hill slopes would then move that stuff out. And what will happen is, this divide between this side and this side of the mountain will start to shift. It will move this direction. And the question here is, would this be common? It's absolutely common, because rock types are different. Climates, you have microclimates where you have one side of the mountain that's wet and one side is dry. So mountains and their drainage divides, the peaks themselves, the ridge lines are always shifting. They're moving left, they're moving right, they're bouncing around all the time. So the way to kind of think about this is, these individual peaks, these individual ridge lines, the individual mountains, these things are short-lived because they're bouncing around as one weathers and hill slopes greater than other sides of the mountains. It's pushing around. But the overall mountain range itself can persist for millions of years as long as your rate of rock input equals the rate of weathering, hill slope, and fluvial sediment taking off it. Mountain fountain. This is just a cool shot. This is of the Alps in France. I took this picture many moons ago. Beautiful mountain range. I strongly encourage you guys to get out there and see the world, see some of this stuff for yourself. It should blow your mind, right? Look at this mountain fountain, right? Boom. That thing is huge. A lot of rock has gone into this thing, weathered, eroded, and come off of it. Okay, so this is sort of funny. Let's go on a road trip to Racetrack Playa. I'm just trying to have fun with this. Racetrack Playa is just one of these super cool geomorphic sites here in North America. That's me in my younger days. This is a Pepsi's Best. As you head out there, you pass something called Tea Kettle Junction, and you're about 6 miles away from Racetrack Playa. A playa, it's this basin right here. Basically, if we were in a wet climate, this thing would be a lake. But because we're a dry climate, the water that pours into this thing evaporates really quickly off, and so it's just this pan of mud. Okay, it's just this mud, super flat surface, actually the flattest surface on the planet. Now, it does get water in it temporarily, but that water evaporates, or it actually, in this case, it mostly percolates down into the ground, so it doesn't persist for very long. This is the grandstand. It's just this really cool piece of bedrock that sticks through the playa surface. Place is awesome. If you ever get a chance to go out there, you got to check it out. And the reason it has that name is because these rocks are on it. So somebody scratched that number on it, which kind of bugs me. But these rocks slide across Racetrack Playa. Okay, now if you were to walk out here and step on this stuff is rock hard. No, not rock hard, but super hard. But what'll happen is the rocks come off this hill slope here. They dump onto the playa. Water comes in, and then all this mud gets super slick, and then winds will come screaming through this low saddle right here and literally blow the rocks across the surface of the playa. Absolutely cool. But nobody's ever seen it happen, so you can make $1 million if you get out there and see it happen for the first time and put it on YouTube. Mookie Marbles. Just telling you guys, geomorphology gets crazy. Krumholtz, what are we talking about? Super old fat tree with flat top. Really strong winds kind of prevent this tree from getting tall. That has nothing to do with geomorphology. I just think it's cool. So what else we got in geomorphology? This is kind of the tail end of the course. We don't have a whole lot more to talk about. I didn't have time to talk about coastal processes, aeolian processes. I'm going to talk a little bit about glacial processes, even though we're nowhere near a glacier here in Phoenix, Arizona. They're just cool. Glaciers are fascinating because it's a pile of ice. And we all get the idea that the ice moves from up here and moves down here. But what's neat is the ice also rotates. And the reason why is up here above the equilibrium line you get an accumulation zone. And this is where snowfall builds up throughout the years, right? The snow falls here, but some of it persists. It doesn't melt in the summertime, so that when it snows again in the winter, it piles up. And that weight of that stuff piling up pushes down and causes it to rotate out here where you have the opposite, where this gets snowed on, but it always melts off in the summertime and you lose the ice. So it's this kind of balance where you get a positive balance of snow up here, a negative balance here, where you have a double direction flowing down and rotating. Okay, there are some cool features associated with glaciers I just want to chat about real quick. These guys are called roches montanées, which is French for rock sheep. Probably not saying that right at all. But what happens is the glacier heads this way. It has a bunch of rocks that it's moving along, and it scours the back half of like some kind of bedrock knob or something, makes it really smooth. But on this side, it gets all chunked up because the ice gets under a lot of pressure as it hits this feature, and the ice will melt under that pressure. And the super pressurized water moves over the rock over here where there is there's no pressure pushing it against the rock, so it refreezes and it breaks the rock apart. You end up with these giant features. Roches montanées. Glaciers move more sediment than any other erosive process. They're just rivers of ice. This is kind of a cool image. You can see this is due to the varnish. These are different depositional features of glaciers called moraines. As the ice moves down, it's just like what do you call those things at a grocery store? Conveyor belt. Just moves rocks and dumps them off, moves rocks, dumps them off, moves rocks and dumps them off, and then piles up in front of the glacier because the ice is always moving, even if the glacier front isn't moving. And if the glacier stays in the same spot for a long period of time, it just dumps and dumps and dumps. Really effective at moving rock. And also as it moves, all this rock over the surface that it's carrying in its frozen water ice, you'll polish rock. This is a really polished stone with striations from rock grinding across it when the ice was over this rock. The sheen right here is this kind of polished rock that's getting glinted off by the sun. Super cool. Here's a retreating glacier in the Alps. Most glaciers on the planet are retreating. So it's tough to see, but on the sides here, there's all this rock and debris that has been moved by this ice over time. These things are just really effective agents of erosion. This is the upper part of that glacier, and this again is in the Alps. Super place to explore. Here's some more features. This is a big, massive terminal moraine. The glacier was here in the past, and it just dumped all the rock right here. Now the glacier has retreated back. The same right here as well. Down here along the flanks you have a lateral moraine. There was glacier ice up to this area. It's dumping all this rock, and now the ice has retreated back. I've already shown this picture before, or at least a picture of this boulder, but this thing is huge. Again, I stand up to about here, and a glacier can move that rock like it doesn't even think twice about it. I mean, glaciers can just move anything. So how do they affect the geomorphic system? Well, they are the super effective hill slope transport. Whatever weathering generates, it's gone. So they're great at removing any weathered stuff, exposing more bedrock. They'll rapidly accelerate the rate at which a mountain will weather and erode. That's why they're one of the reasons a lot of the big mountains in the world are going to be in the tropics, because you have to be really high elevation before you start getting glaciers. And because if you have something like Mount Everest up north, like in Antarctica or Alaska or something, glaciers would just be chowing away at that thing, and it wouldn't be as tall as it is today. So glaciers are kind of like the heavyweight champs of erosion. There's another cool picture of a glacier. This is a cool shot. All the bedrock here, that's all cleaned off. The glacier used to be up to this area. The glacier is now gone, but this was all filled with ice up until this point. This talus slope was basically in equilibrium to the glacier surface right there, and now it's gone, and all we're left with are these lakes, these tarn lakes. Okay, so that's it. Here's our things to know. What is landscape evolution? I need you guys to know the geomorphic system diagram. How do weathering hill slope processes and fluvial processes interact with each other to generate weathering limited landscapes, transport limited landscapes, pediments, and alluvial fans? How do landscapes respond to climate change, earthquakes, wildflower, drainage divide, retreat? And how do glaciers interact with landscape evolution? Hope you've enjoyed this, guys. Class is almost done. Thanks for everything. See you in lab.